Hello, I am Tatiana Benavides, manager of the Space Innovation Hub at ETH Zurich. In this lecture, we will cover the following aspects of space for circular economy. First of all, what is circular economy? Then, circular economy in space, digging into the life support systems in space, particularly at the International Space Station, and moving farther away to the Moon, Mars, and as an example of an initiative by ESA, the European Space Agency, of a closed-loop system called MELISA, standing for Microecological Life Support System Alternative. Before concluding, we will go through the terrestrial applications of such systems and end with other examples of circular economy. What is circular economy? A circular economy system is a cycle where the produced goods are consumed by the user and then come back to the production line as raw materials used in manufacturing. In contrast, linear economy does not recycle or reuse the materials after consumption, resulting in the generation of waste and pollution. It goes from a natural resource being manufactured into a product which is destined to become waste after consumption. By recovering the consumed product and turning it into the source that fits into the production line, circular economy takes into account the sustainability aspect and tackles global challenges like climate change, biodiversity loss, as well as reducing waste and pollution. Circular economy in space. What do we need to survive in space? Think about the things that we have on Earth that we take for granted, such as the air we breathe, the oxygen, the food we eat, and of course, water. These are the basic needs that need to be fulfilled first when bringing astronauts to space to ensure their survival. And what happens with our waste after we eat or drink something? Urine, feces, carbon dioxide, transpiration. On Earth, we have working pipe systems, at least on many places, but still critically missing in others. But in space, we have to provide a self-sufficient system to take care of the waste, what we call waste management. Taking proper care of waste and controlling the environment is crucial as dangerous amounts of carbon dioxide, untreated urine and feces, would be toxic and threaten the astronauts' lives. So what we need is food and water production, a waste management for treatment and recycling of the waste, and atmosphere monitoring and control to provide oxygen and remove carbon dioxide. Here we have a picture on the left of the International Space Station, called ISS for short, and on the right you see a life support system example. It is an interior view of the Leonardo multipurpose logistics model, carrying the two water recovery system racks for recycling urine into potable water and a second toilet system, amongst other materials for the ISS. The ISS recycles most of its air and water. Through water electrolysis, oxygen is produced from water using electricity. The oxygen is breathed by astronauts, which in turn produce carbon dioxide. And carbon dioxide, as it's toxic for humans in high levels, it has to be removed from the atmosphere through the environmental control system. The Advanced Closed Loop System, ACLS, from ESA recycles carbon dioxide on the space station into oxygen. Previously, oxygen on the space station was extracted only from the water that is supplied from Earth. But with the new system, half of the carbon dioxide is recycled, saving about 400 liters of water that needed to be launched to the station each year. Although water is recovered from urine and transpiration, it is still continuously resupplied as the current efficiency of the systems at the ISS allow for only about 85% of the water to be recycled. In addition, food is also continuously resupplied from Earth to space, and the waste are returned burning at the re-entry back on Earth. Going deeper, even though urine is separated from the solid waste, only the water in the urine is recovered at the ISS, and all the nutrients contained in the urine are wasted. Urine is actually rich in nutrients like nitrogen and phosphorus needed for growing plants and algae. Thus, a complete urine recycling system would take advantage of these processed materials to fit into the circular economy loop. The further away from Earth and the longer the space missions, the more consumables that would be needed to keep the astronauts alive. Due to the cost, time, and distances in transportation, it is not feasible to resupply long-term space missions with resources from Earth. In the space exploration roadmaps, the next steps include the Lunar Gateway, a station that will be orbiting the Moon in the next years. The long-term vision is to eventually colonize the Moon, having humans living and creating a civilization up there in preparation to then go farther to take the first humans to Mars. With the current technologies, a 3-year mission to Mars with 6 astronauts would require 4 rockets to take all the consumables needed for the astronauts to stay alive throughout the mission duration. This is too expensive and most likely not feasible. As we go farther away from Earth, we need to be independent and produce our own resources, taking care of the waste in a sustainable way. A closed-loop life support system would enable long-term space exploration. Let's see an example of this. An example of a life support system developed for space is the MELISA initiative, standing for Microecological Life Support System Alternative. It started in 1989, inspired by the natural process occurring here on Earth, in lakes including the anaerobic fermentation, photoheterotrophy, nitrification, and photosynthesis. It is a collaborative program between the European Space Agency, academia, and private partners. In the picture, the different cycles are illustrated. In reality, the different biological and chemical processes take place in photoreactors, with compartments integrated for the different species, like for bacteria, algae, and plants, closing the loop with the humans, here illustrated as the crew. As the human waste and carbon dioxide are turning to oxygen, food and water, a complete circular economy system is created. This is how the MELISA pilot plant with photoreactors looks like. It is an external ESA laboratory located in the Universitat Autónoma de Barcelona in Spain. The cycles that take place in the MELISA pilot plant compartments occur naturally in Earth, as our planet acts as a whole closed regenerative life support system, producing water, oxygen, and food. In the biosphere, these complex processes include plants and algae doing photosynthesis, converting carbon dioxide into oxygen using light as an energy source. The water cycle processes called evaporation, condensation, precipitation, and filtration recycle the water. And food production, mostly through agriculture, uses fertilizers coming from animal wastes. The life support systems are needed to enable life in space, but are used on Earth to develop self-sustainable habitats and reduce environmental impact caused by human activities. Coming to the applications outside the space domain, the terrestrial applications, the life support systems enable decentralized services to support city infrastructure like housing and industry buildings, as well as hotels, and mostly useful in places with water shortage and scarce food production, including remotely regions not connected to the main city infrastructure. Being inspired by the limited resources available in space creates sustainable solutions for Earth, particularly for extreme and isolated areas in Earth, like the mountains, deserts, isolated shelters, and the Antarctica. As an example, in the French and Italian Antarctica base called Concordia Station, all the water used for hygiene purposes is recycled. Imagine how clean our cities would be if we all live under this principle. A profitable business model for life support systems in a circular economy fashion would have a market here on Earth targeting clean cities, avoiding food waste, saving resources like water, and reducing energy cost. Other applications for these systems include the microbial factories, as algae can be used to produce biofuel, bioplastics, bioconcrete, carbon fiber, proteins for food supplements, as well as pigments and polymers for manufacturing materials. As a conclusion, life support systems are a perfect example for a circular economy with a sustainable impact, turning waste into food and every generation all in a cycle. Other examples that fit into this circular economy loop are the recycling of materials such as plastic, old tires and rubber waste to produce roads and bricks for constructions. So the use of carbon extracted from trash to produce fuel for transportation, and creating another purpose and reuse either electrical devices themselves or their components, as well as any other businesses that use recycled content and recyclable materials in their products. With this, we close the Space for Economy lecture. I hope you enjoyed and got some insights on how technologies needed for space can be used to improve the life here on Earth in a sustainable manner.